Welcome to this problem-solving session. Today, we'll dive into problem number 386, titled Lexicographical Numbers. This problem challenges us to think critically about ordering numbers in a lexicographical sequence. Let's preview the approaches, techniques, and key takeaways you'll gain by solving this problem. This problem asks us to generate a list of integers from 1 to a given number n, but the twist is that the numbers need to be sorted in lexicographical order. Lexicographical order is essentially dictionary order, where numbers are compared based on their string representation. For example, 10 comes before 2 because 1 is smaller than 2 in the first character position. The input to the problem is a single integer n, where n can range from 1 to 100,000. The output is a list of integers sorted in this lexicographical order. Let's take a look at a few examples to clarify this requirement. In the first example, we are given n equals 13. The numbers from 1 to 13 are 1, 2, 3, 13. When we sort these numbers lexicographically, the result becomes 1, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7, 8, 9. Notice how 10 appears immediately after 1 because, as strings, 10 comes before 2. Similarly, for the second example, if n equals 2, the range of numbers is 1, 2. In this case, the lexicographical order remains the same as 1, 2, since there are only two numbers, and their natural order matches the lexicographical order. Now, for a slightly larger input, if n equals 25, the list of numbers to consider becomes 1, 2, 3, 25. When we sort the numbers from 1 to 25 lexicographically, the output is 1, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 2, 20, 21, 22, 23, 24, 25, 3, 4, 5, 6, 7, 8, 9. Here, the numbers starting with 1 are grouped together first, followed by numbers starting with 2, and so on. This is the key idea behind lexicographical order. It prioritizes the leftmost digits as if they were characters in strings. The problem also includes constraints to keep in mind. The input n can go as high as 100,000, which means the solution must be efficient in both time and space. Additionally, the output size grows linearly with n, so any overly complex or memory-intensive approach might fail for larger cases. To handle edge cases, consider scenarios like n equals 1, where the output is simply 1, because there's only one number. For values like n equals 10, the lexicographical order becomes 1, 10, 2, 3, 9. Notice how 10 comes right after 1. For very large inputs, such as n equals 100,000, the solution must be optimized to avoid timeouts or excessive memory usage. Small values, like n equals 9, are straightforward since the natural order already matches lexicographical order. However, for inputs like n equals 25, the solution must correctly transition from numbers like 2 to its consecutive numbers 20, 21, 25, before proceeding to 3. This ensures the order remains accurate and consistent with the lexicographical pattern. To solve the lexicographical numbers problem, the first approach we can consider is the brute force method. Here, we generate all numbers from 1 to n, convert each number into its string representation, and then sort these strings lexicographically. Once sorted, we convert the strings back to integers to form the final result. While this approach is straightforward to implement, it has significant drawbacks. The primary issue is efficiency. Sorting the numbers lexicographically has a time complexity of n*log n, and the space complexity is n, because we need to store the entire list of numbers. This makes the brute force approach computationally expensive, especially when n is large, such as 10 to the power of 5. To address these inefficiencies, we move to a more optimized method using depth-first search, or DFS. This approach allows us to generate the result directly in lexicographical order without relying on sorting, making it far more efficient. The optimized DFS approach starts by generating numbers in lexicographical order directly. To do this, we begin with the number 1 and recursively append digits 0 through 9 to the current number, provided the resulting number stays within the range from 1 to n. At each valid step, we add the number to our result list. This process continues until we have traversed all numbers up to n. A key insight here is that lexicographical order corresponds to a pre-order traversal of a conceptual tree. In this tree, each number x serves as a node, and its children are x0, x1 is x9, provided they are less than or equal to n. By recursively visiting these children in ascending order, we naturally generate numbers in the desired lexicographical sequence. The efficiency of this method is notable. The time complexity is O, n, as each number is visited exactly once, and the space complexity is O, log n, which accounts for the depth of the recursion stack. This approach avoids the need for explicit sorting, making it much faster than the brute force method. An alternative to recursive DFS is an iterative approach using a stack. This approach simulates the DFS process without recursion. We start by initializing a stack with numbers 1 through 9. Then, we repeatedly pop the top number from the stack, add it to our result, and push its children onto the stack. Each child is formed by appending digits 0 through 9 to the current number, provided the resulting number is less than or equal to n. This process continues until the stack is empty. The iterative approach has the same time complexity as recursive DFS, O, n, as each number is processed once. However, the space complexity is O, n, in the worst case, due to the stack size. While this method avoids the overhead associated with recursion, it is slightly more memory intensive and can be more complex to implement compared to the recursive DFS. As a result, it is less commonly preferred unless recursion needs to be explicitly avoided. Among the approaches discussed, recursive DFS stands out as the most efficient and elegant solution. By leveraging the structure of lexicographical order and traversing a conceptual tree, we avoid redundant operations such as sorting. The key insight is recognizing that lexicographical order can be directly generated by recursively exploring numbers in ascending order. Compared to the other methods, DFS offers several advantages. It is more efficient than brute force, as it eliminates the O, n asterisk log, n, sorting step. It is also simpler to implement and understand than the iterative stack-based DFS, while maintaining lower memory overhead, with a recursion depth limited to log n. While brute force is straightforward, it quickly becomes computationally expensive for larger inputs. On the other hand, the iterative DFS requires more memory due to the size of the stack. Recursive DFS strikes the best balance, offering efficiency, simplicity, and minimal space requirements, making it the most practical choice for this problem. After evaluating the different approaches, the recursive DFS method is chosen as the final solution due to its optimal time complexity of O, n, low space complexity of O, log, n, and ability to generate lexicographical order directly without sorting. These characteristics make it the most efficient and practical solution, especially for large inputs up to 10 to the power of 5. The elegance of this approach lies in its simplicity and efficiency, providing a robust way to solve the problem while avoiding the pitfalls of alternative methods. This makes recursive DFS the clear winner for tackling the lexicographical numbers problem. To solve the problem of generating integers from 1 to n in lexicographical order, we can start by understanding a simple brute force approach. First, we generate the range of numbers from 1 to n. This ensures that all integers within the specified range are considered. For example, if n is 13, this step produces the numbers 1, 2, 13. Once we have these numbers, the next step involves converting each of them to their string representation. This is a critical step because lexicographical order is based on string comparison rather than numeric comparison. For instance, when treated as strings, 10 comes before 2 because the first character of 10, which is 1, is smaller than 2. After converting the numbers to strings, the next step is to sort these strings lexicographically. This operation ensures that the strings are ordered as they would appear in a dictionary. Finally, we have the sorted list of strings, such as 1, 10, 11, 9, for n equals 13, which prepares us for the next steps of the algorithm. Once the list of strings is sorted lexicographically, we convert the strings back into integers. This final conversion step is necessary because the problem requires the output to be a list of integers. For instance, the sorted strings 1, 10, 11, 9 are transformed back into 1, 10, 11, 9. This gives us the final result, which can now be returned. However, while the brute force approach is straightforward, it becomes inefficient for large values of n due to the cost of sorting all the numbers. To address this, we can use a more optimized approach based on depth-first search, or DFS. With DFS, we directly generate the numbers in lexicographical order without the need for explicit sorting. The process begins with the initial digits from 1 to 9, which are valid starting points for lexicographical order. For example, when n is 13, the algorithm starts by considering numbers like 1, 2, 3, and so on. These initial digits act as the roots for exploring further numbers through recursion. As the DFS proceeds, we recursively generate numbers by appending digits from 0 to 9 to the current number. The key here is that we only append digits if the resulting number does not exceed n. For instance, starting with the digit 1, we can append 0 to form 10, then append 1 to form 11, and continue as long as the numbers remain valid. If a number exceeds n, the algorithm backtracks and tries the next digit. This backtracking ensures that we avoid unnecessary computations and only generate numbers within the valid range. Each valid number is added directly to the result list. Since the numbers are generated in lexicographical order during the DFS traversal, no additional sorting is required. The recursion ends once all numbers up to n have been processed, and the final result list is returned. This optimized approach not only avoids the computational overhead of sorting but also ensures that each number is processed exactly once, making it highly efficient. To implement these approaches, we rely on a few key data structures. The final result is stored in a list, which is returned at the end of the algorithm. In the DFS approach, a recursive stack is used to manage the backtracking process. This stack enables the algorithm to explore one branch of numbers at a time, returning to previous states as necessary. For the brute force approach, string conversion is a crucial step for lexicographical sorting, but this step is not required in the DFS approach. By avoiding string conversions in sorting, the DFS method achieves better performance, especially for large values of n. In terms of space complexity, the DFS approach is efficient since it only uses the recursion stack, while the brute force approach requires additional space to store and sort all numbers as strings. Overall, the DFS method combines simplicity and efficiency, making it the preferred choice for solving this problem for large inputs. The provided code solves LeetCode problem number 386, lexicographical numbers, efficiently using a depth-first search (DFS) approach. 1. Class and method. A class solution is defined, containing the method lexical order. This method takes an integer n as input, representing the upper limit of the range of numbers to be processed. 2. Result list. An empty list result is initialized to store the numbers in lexicographical order. 3. DFS helper function. A nested function DFS current is defined to recursively generate numbers in lexicographical order. If the current number exceeds n, the function returns immediately, ending recursion for that branch. The current number is added to the result list. A loop iterates through digits 0 to 9, constructing the next underscore number by appending the digit to current, i.e., current asterisk 10 plus I. If next underscore number exceeds n, the loop breaks early to avoid unnecessary recursion. For initial DFS calls, the outer loop in lexical order iterates through digits 1 to 9, since numbers cannot start with 0. For each digit, the DFS function is called, initiating the recursive generation of lexicographical numbers starting from that digit. 5. Result return. Once all DFS calls are complete, the result list contains all numbers from 1 to n in lexicographical order, which is returned as the final output. ###key insights. The DFS approach is efficient because it directly constructs numbers in the desired order without sorting. This avoids the overhead of generating all numbers first and then sorting them. The recursive structure ensures that each number is processed fully before moving to the next, maintaining the lexicographical sequence naturally. The early termination condition, if next underscore number n, optimizes performance by pruning unnecessary branches of the recursion tree. ### complexity. Time complexity. The algorithm visits each number exactly once, resulting in O(n) operations. Space complexity. The recursion depth is proportional to the number of digits in n, giving a space complexity of O log n. This implementation is concise, efficient, and handles the problem requirements effectively. Here, we are implementing a solution to generate lexicographical numbers using Java. The method lexical order takes an integer n as input and returns a list of integers in lexicographical order from 1 to n. We start by creating a list integer named result to store our output. Next, we define a helper function DFS, which stands for depth first search. This recursive function takes an integer current as its parameter, representing the current number we're processing. The first condition in DFS checks if current exceeds n, and if it does, we simply return to stop further recursion. Otherwise, we add the current number to the result list. Then, we iterate through the digits 0 to 9, constructing the next potential number by multiplying current by 10 and adding the digit I. If this new number exceeds n, we break out of the loop to avoid unnecessary recursion. Otherwise, we recursively call DFS with the new number. Once the depth first search function is defined, we initiate the process by iterating through the numbers 1 to 9. For each of these numbers, we call the DFS function, which begins the recursive exploration for that branch. This ensures that we build the lexicographical order starting from each number in this range. Finally, the method returns the result list containing all numbers from 1 to n in lexicographical order. This implementation leverages recursion to systematically traverse through all valid numbers while adhering to the required order. Here, we start with an example where n is equal to 13, and our task is to generate numbers from 1 to 13 in lexicographical order. The process begins with an initial setup. We initialize n as 13 and an empty list called result. Then, we enter the first for loop, where the variable I ranges from 1 to 9. In the first iteration, when I equals 1, we call the depth first search function, DFS, with the argument 1. Inside DFS, the current number is 1, so we add 1 to our result list, making it 1. Next, we enter an inner for loop where we calculate the next possible number by multiplying the current number, 1, by 10 and adding values from 0 to 9. The first calculation gives next underscore number is 10, and since 10 is less than or equal to 13, we make a recursive call to DFS with 10. As we proceed, the recursive call to DFS with 10 sets the current number to 10, which is then added to the result list, updating it to 1, 10. Within this call, we again enter the inner for loop to compute the next possible number. The first calculation gives next underscore number as 100. Since 100 is greater than 13, we break out of the inner loop and return to the previous DFS call, where the current number was 1. Back in that call, we increment I in the inner loop, resulting in next underscore number being calculated as 11. Since 11 is less than or equal to 13, we make another recursive call to DFS with 11. In this new call, the current number is 11, which we add to the result, updating it to 1, 10, 11. Similar to before, we calculate the next number, which is 110. As 110 exceeds 13, we break and return to the previous DFS call. Continuing from where we left off, we increment I again in the inner loop of DFS, 1, and the next number becomes 12. Since 12 is less than or equal to 13, we call DFS with 12. In this call, the current number is set to 12, which is added to the result list, making it 1, 10, 11, 12. The inner loop calculates the next number as 120, and because 120 exceeds 13, we break out and return to DFS, 1. Back in DFS, 1, we increment I once more, resulting in next underscore number being 13. As 13 is equal to the upper limit, we make a final recursive call to DFS with 13. Here, the current number is 13, which is added to the result, updating it to 1, 10, 11, 12, 13. The next number, calculated as 130, is greater than 13, so we break and return to DFS, 1, completing this branch of recursion. Now, we return to the outer for loop, where I increments to 2. A call to DFS, 2, is made, setting the current number to 2 and adding it to the result list, which becomes 1, 10, 11, 12, 13, 2. In the inner loop of DFS, 2, we calculate the next number as 20. Since 20 is greater than 13, we break out and return to the outer loop. The process repeats for I equal to 3, 4, and so on, up to 9. Each of these values is added to the result list directly, as their next possible numbers always exceed 13 and no further recursive calls are made. Finally, combining all iterations, the result list becomes 1, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7, 8, 9. This completes the construction of lexicographical order up to 13. In this second example, we extend the range to n equals 25. The initial setup follows the same pattern. We initialize n as 25 and result as an empty list. The outer loop begins with I ranging from 1 to 9. The process of recursive depth-first search remains similar to the first example, but now we include additional numbers such as 20, 21, 22, 23, 24, and 25 in our result. For instance, when DFS is called with 2, numbers like 20 through 25 are recursively explored and added to the result before moving to the next value of I in the outer loop. Eventually, the final result list is constructed as 1, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 2, 20, 21, 22, 23, 24, 25, 3, 9. This demonstrates how the algorithm adapts to handle larger ranges while maintaining lexicographical order. The time complexity of this solution is O(n), where n is the input number, and this is primarily due to the depth-first search traversal. Let's break it down. The DFS function visits each number between 1 and n exactly once, appending each number to the result list during its visit. This means there are O(n) visits in total. Now, during each visit, the function iterates through up to 10 possible children, corresponding to the digits 0 through 9. However, the condition if next underscore number n ensures that not all 10 children are explored, especially for numbers closer to n. This optimization keeps the total number of iterations proportional to n. Additionally, the outer loop iterates from 1 to 9, calling the DFS function for each starting digit. But since the DFS already ensures every number is visited once, this outer loop does not add extra complexity. As a result, the overall time complexity is dominated by the DFS traversal, making it O(n). The space complexity of the solution is O log n. This is because of two primary factors, the recursive stack and the result list. First, the depth of the recursion corresponds to the maximum number of digits in any number between 1 and n. The number of digits in a number is determined by its logarithm base 10, so the recursion depth is O log n. Second, the result list stores all numbers from 1 to n, which requires O(n) space. However, because the result list is part of the output and not auxiliary space, it does not contribute to the auxiliary space complexity. Therefore, the auxiliary space complexity is determined solely by the recursion stack, which is O log n. When comparing this optimized DFS approach to a naive solution, we see the clear benefits. A naive approach would generate all numbers from 1 to n and then sort them lexicographically. The sorting step introduces a time complexity of O(n) log n, and the space complexity is O(n) due to the storage of the list. In contrast, the optimized DFS approach generates the numbers directly in lexicographical order, eliminating the need for sorting. This reduces the time complexity to O(n) and the auxiliary space complexity to O log n. Furthermore, the time complexity of O(n) holds consistently across best, average, and worst cases, as every number between 1 and n is visited exactly once. Similarly, the space complexity remains O log n in all cases, as it depends only on the recursion depth, which is determined by the number of digits in n. To mathematically prove the time complexity, note that each number between 1 and n is visited exactly once, and each visit involves a constant amount of work, such as appending to the result list and checking the children. This means the total number of operations is proportional to n, confirming that n equals O(n). When working with lexicographical numbers, there are several common mistakes to be aware of. First, a frequent error is confusing lexicographical order with numerical order. Remember, lexicographical order treats numbers as strings, so 10 comes before 2, which can lead to incorrect outputs if this distinction is overlooked. Another issue arises from inefficient string conversions. If you repeatedly convert numbers to strings inside a loop, it can create significant performance overhead, especially for large values of n. Instead, consider pre-processing and storing string representations to save time. It's also important not to overlook edge cases. Scenarios like n equals 1, n equals 0, or very large n, such as 10 to the power of 4, can lead to out-of-bound errors or inefficiencies if not handled carefully. Finally, be cautious about sorting the entire dataset when you're only looking for partial results, such as the top k elements. Using a full sort wastes computational resources. Instead, opt for a more efficient method like a heap or quick select for partial sorting to save time and memory. Another mistake to avoid is failing to optimize for constraints. Relying on a brute force approach might seem straightforward, but it often exceeds time limits for large inputs, especially when more efficient solutions are possible. Speaking of efficient solutions, a key observation is that lexicographical order aligns with a pre-ordered traversal of a tree, where each node corresponds to a number. This insight is crucial because it enables the use of recursive or iterative depth-first search methods to generate results efficiently. Interviewers often expect solutions better than O, n log n, so exploring DFS or even heap-based approaches can make your solution stand out. Additionally, it's a good idea to discuss edge cases proactively during interviews, such as handling small values of n, large values, or even repeated numbers if they're relevant. Lastly, when deciding on an approach, be ready to explain the trade-offs. While brute force may be simpler, optimized solutions often require more thought but demonstrate a deeper understanding of the problem. A clear explanation of your reasoning can make a strong impression. Now, let's look at related problems that share similar concepts or techniques. For example, LeetCode 315, count of smaller numbers after self, and LeetCode 442, find all duplicates in an array, involve sorting and traversal techniques that may overlap with ideas used in lexicographical order problems. Similarly, LeetCode 658, find k closest elements, emphasizes efficient handling of subsets and partial results, which is a useful skill for this topic. In terms of alternative approaches, a brute force method involves generating all numbers from 1 to n, converting them to strings, and then sorting them lexicographically. While this approach is simple and straightforward, it has a time complexity of O, n log n, making it inefficient for large values of n. A more refined approach is to use DFS, which simulates a pre-ordered traversal of a virtual tree where the children of a node x are 10x, 10x plus 1, and so on. This method operates with a time complexity of O, n, making it far more efficient, but it does require careful implementation to ensure edge cases are handled properly. Additionally, a heap-based approach can be useful in certain scenarios. By using a min-heap, you can maintain the smallest k elements in lexicographical order, which is particularly beneficial when you only need partial results rather than the full list. However, while this method has a time complexity of O, k log k, it's not optimal for generating the entire sequence. Ultimately, the choice between these approaches depends on the specific requirements of the problem, such as whether you need all elements or just a subset. Each method has its trade-offs in terms of simplicity, efficiency, and implementation complexity, so it's important to choose the one that best fits the constraints and goals of your solution. Great job making it to the end. Today, we reviewed lexicographical numbers, explored its brute force solution, and highlighted important concepts like lexicographical ordering. Remember to keep practicing similar problems to strengthen your algorithmic skills. Thanks again for joining, and I'll see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!